Hello everyone, let's solve some LeetCode today. So today we have this implement queue using stacks problem. It's a LeetCode 232 problem and we are going to solve it with help of two solutions. Now let's look at the problem. Implement a first in first out, that is queue, using two stacks. The implemented queue should support all the function of a normal queue: push, peek, pop, and empty. Implement the myQueue class with the help of these operations. Now we have these nodes. So you must use only standard operation of a stack, which means push to pop, peek, pop from top, size, and is empty operations are valid. So we cannot really index the elements in the stack. People might actually try to implement stack itself using arrays, and they might actually try to use indexes to hack their way around it. So that's what they are saying, that no, you're not supposed to do that. If you're doing it, it's kind of cheating, but you are only supposed to use the standard function of a stack, that is pop, push, peek, or top, or size, and is empty. Now depending on your language, stack may not be supported natively. You may simulate a stack using a list or a deck. Deck means dequeue or double-ended queue, as long as you use only stack's standard operation. Okay, so they are saying that if your language of choice does not really support a pre-built or built-in data structure called stack, you can simply create it yourself with the help of these, either list, that is linked list, or a dequeue, that is double-ended queue. Now let us try to solve it. So basically, what is a queue? Queue is a data structure where the first in and first out principle applies. Suppose that we have few elements, 1, 2, and I started adding elements like this. First I add 1, so 1 is here, then I add 2, then 2 comes here, then 3, then 4. So when I'm pushing elements into the queue, they are getting pushed at the end of the queue, not at the start of the queue, right? When I actually try to say, pop an element from the queue, then I'm not going to pop 4. That is wrong. I'm gonna pop 1. So 1 will be removed. Now once the 1 is removed, 1 is no longer there. Simple as that. Now what we have in the queue is 2, 3, and 4. If I say that, okay, pop again, then the 2 will be removed, this will be removed, and similarly the 3 will be removed and the 4 will be removed in this order. Of course, pushing is always gonna happen at the end. So now that we have removed 1 and 2, suppose I want to push 1 again. So 1 will go at the end of the stack, that is at this place. Okay. If I then again try to push 2, then it will go to this place. And the problem right now that we are facing is that when we are using a stack, if I push 1, 1 will come here. If I push 2, then 2 will be here. If I push 3, 3 will come here, then 4. If I'm pushing here, then the first element in the stack, as you can see, is the last element that we pushed. And then if we try to pop it, then the 4 will be popped. Okay, but we are not supposed to pop the 4, because 4 is the last element that we pushed. We are supposed to pop 1 because it is the first element that we pushed in the stack. So this is basically the problem that we are facing. So now let us try to think what will happen if we have another stack here. Well, I want to pop 1, right? So in order to pop 1, I need to get rid of these elements. So I need to get rid of them, but I don't want to lose them, because if I lose them, then I am losing the data, right? What is the point of losing data? So what I can do is I can say that, okay, you know what? Pop this element 4 and then push it here. Then what will happen is that I will have 4 at the bottom, 3 will come here, 2 will be here, and then I can also again pop 1, and the 1 will be at the top. Now as you can see that in this new stack, the 1 is at the top because the order of the elements is now reversed. So now if I can say pop on the second stack, then the second stack will pop actually 1. So 1 will be popped, and then what I can do is, once the 1 is popped, this is now gone, it's no longer there, and this is empty. Now what I can do is I can pop everything back. I can say, you know what, 1 is gone, so let's pop 2 again into the original array. 2 comes here, then 3, and similarly 4. And the second stack now becomes empty. It's no longer there. So this is the kind of logic that we can use for pop. For push operation, it's an order of 1 time complexity, because we are simply gonna push everything in this stack. But when we are popping, first we have to move every element from this stack to this stack, pop, okay, the first element that is present in this stack, and then pop rest of the elements back into this. So it's basically a time complexity of order of 2n, which eventually becomes order of n. That's what the time complexity of pop is right now. Now let us try to look at the peek operation. The time complexity of push is still, order of 1. So time complexity of push is order of 1 because we are simply pushing. So for peek operation, we will again have to do the same thing. And that is because if I actually say that, you know what, I want to peek from the data, then what I really want to peek is the 2, but what I have at the top is 4. So eventually I will again have to pop everything in this original array into the new array like this, and then peek from there, because now the order will be reversed. The order will be like 2, then 3, and then 4. I will get the peak element, that is the top element, and then I will again have to, pop everything back. So the order will again become 4, 3, 2, because we are not popping 2, so the 2 will still be here. So in this way, the peak's time complexity will also be equals to order of n, right? Because it's basically the same algorithm we are using. Now for is empty, this is going to be order of 1, because we are only going to go ahead and see, if this stack is empty or not. If this is stack is empty, then we can say that, there are no elements in the queue and it's an empty queue. So it's a time complexity of order of 1. It's gonna be constant, simple. So this is how we can implement queue using two stacks. Now this solution currently is very unoptimized solution, because we have order of n time complexity for pop and for peak both. So can we make it a bit more optimal? And the reality is that yes, we can make it a bit more optimal. We can reach a solution where the time complexity for pop is order of 1 and the time complexity of peak is also order of 1. The time complexity of push will become order of n. How does that work? Well, let's try to figure it out. So we have 1, 2, 3, and 4. These are the elements that we have. We have only one single stack. Okay. Now just think about it. If I actually have something like this 4, 2, 3, and 2 and 1. Now, if I want to pop the first element, I can simply pop it, right? Simple as that. It's going to be normal operation, right? Also, if I want to peek it, it's also going to be simple, right? Because it's the first element. And this is when, when we started adding from 1. I add 1, then 2, then 3, then 4. But the order of elements in the stack becomes 4, 3, 2, 1. That is reverse. Then the time complexity for these operations will become order of 1. So how can we really do that? And the answer lies in the push operation. So when we are pushing the elements, we can actually reorder the elements. In the push operation, we will have a global stack. Okay, this is the global stack that we are going to use to pop and peek elements. But we will again have a local stack in the function itself. Now what we can do with the help of this local stack, okay, so it's a local stack and it's a global stack. So suppose that we already have a few elements in the global stack. Suppose we have 1, 2, and 3. Now we want to push 4. So what we will do is, first of all, we will start popping these elements. We will pop these elements and put them here. So 1 will come here, then 2 will come here, it will become 2, and the 3 will come here. 3 is now here. Now that I have 4 here, I'm trying to push 4 element here. I can simply directly push it in this place, right? And currently the global stack is empty. And now what I will do is I will push 4 at the bottom, then the 3 will go here, then the 2, and then 1. So as you can see that the last element that we pushed into the queue is actually at the last position in the global stack. Yes, here we actually had a reverse order in the local stack, but in the global stack we do have the correct order. So the first element is at the first position, the second is at the second position, the third is at the third, and the fourth, that is the last pushed element, is at the last position. So now if we pop, then the first will be popped first, or the first will be peaked. So we actually ended up making the pop time complexity is equals to order of 1. Similarly, for the peak also, peak is also now order of 1, but the time complexity for push is now order of 2n, because first of all we actually move everything from here to here, we push the element, right, and then we move back everything from here to here. So it will become 2n, that is basically the same as order of n, because 2 is a constant, so we can ignore it. So now we basically have three operations that are at order of 1. Now in the question, if you go at the end, you will actually see this paragraph, that is follow up. Can you implement the queue in such that each operation is amortized order of 1 time complexity? In other words, performing an operation will take overall order of n time complexity, even if one of those operations may take longer. So what is this amortized order of 1? Well, it is basically the average time complexity. So what they're saying is that, in each operation, you can take order of n, but the overall time complexity for all the operation will become on an average order of 1, that is constant time complexity. So let us try to understand it. Okay, so here in the original solution we actually had two stacks, right? Let's make them again. We again have the same elements 1. Now suppose that we started pushing every element in this stack, that is s1 and s2. We have two stacks, right? So 1 is pushed, then 2 is pushed, then 3, and then 4. Now I want to pop. So push till now is order of 1, correct? Now I want to pop an element. So I need to pop 1, but I have 4 at the top. I will simply move all the elements into this stack. So the order will become 4, 3, 2, and 1. So this takes around order of n complexity, correct? Now I can simply pop from here and it takes order of 1. Pop now takes order of 1. This one, right? Now the thing is that this array is now, this stack is now actually empty. There is nothing here. And we have elements in the S2. Now we are not popping back again. We are not actually doing this. This step is now prohibited. Now suppose that there is another element that comes here, that is 5. 5 I want to push. Now where do I push? That is the question. Should I push here or should I push here? Well, if I push it here, then it will come at the top. That is, it will actually mess with the order that we already have in this stack, right? 5 should be at the bottom, but it is at the top. So we cannot really push it here. It will mess with the order. So what I will do is I will push it in this stack. So this stack will, so 5 is pushed in the original stack. Simple. And in case if some other element also come, I will, keep pushing them in this stack. That is, it will become 5, 6, and 7. Okay, it will become like this. Simple. Now the push operation at this point is running at order of 1 time complexity, correct? Now if I try to pop something again, so as you can see that we still have elements in this S2 stack. So I can simply go ahead and pop. So 2 will now be popped. So 2 is gone, 1 is gone, 2 is gone, right? So it also actually became 1 because now we don't actually have to move elements every time that we pop. We move element once and then we keep popping from this stack until unless the elements become 0. Once we pop 3 also and we pop 4 also, now this stack actually is empty. So we can no longer directly pop from this stack. So we now then take all these elements, push them into this stack. So now the stack will become, now we can actually keep popping. So these elements will be gone from here. So now I can pop 5. So in this approach, we don't actually have to shift elements every single time I run a pop operation. As long as there are some elements in this part of the array, I can keep on popping and I can keep on pushing here anyways with the order of 1 time complexity. So currently it is kind of messy, right? Sometimes we run this loop order of n to shift everything into the new S2 stack and then pop. Sometimes we simply pop from the S2 stack because there is element. So what is the real time complexity of this pop operation? Let's try to observe it because mathematically doing it will become very tedious. So let's try to observe it. So suppose that we have again two stacks, that is S1 and S2. Now we have a few elements, that is, now we want to pop one element. So this needs to be popped, right? Because it is the first element that we added. So I will give them here. So it will become 3, 2, 1. And then I can start popping. So this will be popped, then this will be popped, then this will be popped. So if I want to pop all the elements, so for popping all the 3 elements, how many operations did I do? It took me around 3 operations to pass elements from this to this, and then it took me one operation to pop this one operation to pop this one, and one operation to pop this one. So all in all, in order to pop one, it took me one operation to take this element from this stack to this stack, and then one operation to pop it from this stack to. So it took me around 1 plus 1, that is 2 operations per element to actually pop it from the queue. So popping one element took me around 2 operations. Here we have n elements, so we can say that it took me n, okay, n operation to take them to the new stack, and then again 1 plus 1 plus 1, it took me n operation to basically pop them. So it took me a total of 2n operation to pop all the elements. To pop n elements, it took me 2n operations. Can we say that? Yes, we can. I can say is that the pop time complexity is right now n. Order of 2n is equals to order of n. Pretty much the same. Order of 2n is basically order of n. Now the thing is that I can at this point say that for n elements it took me an order of n time complexity to actually achieve the pop result, right? Which means for each and every element it took me how much? One operation. Even if I even if I say that it took me 2n, then I can say that for each it took me 2, right? Which is a constant. It's a constant, right? For each I am not taking an operation to pop each element. I am taking only 2 operations on an average to pop one element from the queue. So I can say that for n elements, I am taking almost n order of n time complexity, which means for each pop, for one pop, what I'm taking is order of 1. So for each pop, on an average, the time complexity will become order of 1, that is constant time complexity, because for an element, it took us an operation. So for one element, it will take us one operation at average, at scale, when we are talking about a lot of elements, a lot of elements. Okay. So on average, it will now give us order of 1 time complexity at this point for popping every element in the queue. And then again, the push is still, going to be pushed into the original array, that is S1. So it will take order of 1. The peak will also take amortized, or average order of 1 time complexity, because the logic comes directly from here. Popping and peaking logic is directly from here. Okay. Well, is empty will also be order of 1, because all we have to do is check whether the S1 is equals to 0 and S2 is equals to 0. If there are no elements in both the arrays, we can say yes, it is empty. Otherwise, if there is even a single element in any of the array, we can not say it is empty. So it's also order of 1. So basically, we reached a point where pop, peak, push, and is empty are all order of 1. Push and is empty are absolute order of 1, and peak and pop are basically amortized or average order of 1. So here's the code for it. In terms of code, it is very simple to actually implement it. First, we have a stack. It is the original stack. Then we have a pop stack. So pop stack is the stack that we are going to use to pop the elements. When we are pushing the element, we are directly pushing it to the stack, that is this original stack. Now when it comes to pop operation, what we are doing first is we are checking if the pop stack's count is 0 or not. If the pop stack have some element, its count will not be 0. We will simply pop from the pop stack. If its count is 0, it does not have any element, what we will do is we will start popping from stack and pushing it to the pop stack until and unless the original stack becomes 0 or empty, and then eventually we will pop from the pop stack. Same logic is applying for the peak also. It's just that at the end I'm just peaking, not popping. And then for is empty, I'm simply checking stack.count and pop stack.count. Both should be 0 for empty to be working. Now if I submit it, it should work, and as you can see that it is working. So I have another solution for you also. Here we are only using single stack in the global, and what we are doing is that in the push function, what we are doing is we have a local stack here, and in the local stack what we are doing is we are first of all taking the global stack, we are popping everything from the global stack, and then we are pushing it in the local stack, and then we are basically pushing the x element in the global stack, and then we are pushing every element from the local stack back into the global stack, and that's taking order of n time complexity, and that is why the rest of the elements are actually order of 1 time complexity absolute, because this solution is basically the same as this one, the one that we discussed here. Pop everything, we push, and then we pop everything back into the original array. This is the solution that we are writing the code for here. This solution should also work, and yeah, it will also work based on the constraint of the problems. So yeah, if you have some problem that you would like me to solve, comment, and we will meet in the next video. Bye.